Alright, so now we're going to wrap up our discussion on the Bernoulli example, fitting the maximum likelihood equations, and I'm going to do this in the computer program R. So this is the third part, and I'll include the other two parts in the description of this video, as well as the complete playlist that I'm making on this paper, and the link to this paper will all be in the description of this video. Okay, as well as the R code itself. I'm going to go ahead and just copy and paste that in there so you can have access to it there. Okay, so what's going on here? Let's go to our Blackboard, and what I want to do is kind of summarize everything that we've already talked about in Step 1 and Step 2. So then we'll go ahead and pull up R and we'll program this in. So we have our data, our outcome data are Bernoulli distributed, so they're yes/no type data, or 0, 1s, with probability of success P, okay, and they're independent. Then we have Y, which is the sum of these unknown betas, these are what we want to know, right, this is what we want to try to estimate, times X. So X is going to tell us something about the probability of success. Okay, I just want to point out you could write this in matrix notation, which I will do when I program in R. So you just kind of stack all your y's up on each other. You get an n by 1 vector, and then you put x as an n by m vector, and then beta as an n by 1 vector. And you can see that's how you do that matrix multiplication. Okay, so z, the distribution function for z looks like this, where basically this is the probability of success, and this is the probability of failure. Now, in Step 1 video, we showed how this could be written like this. Okay, so basically, these are the same functions, probability distribution for Bernoulli, except this is written in the format of an exponential family type distribution. Okay, but they're the same things. Algebra will show that they're the same, where theta k equals the log of p over 1 minus p. Okay, and again, we showed that in more detail in the Step 1 video. Now, we also showed that you could write this, rearrange this, solve for p, and you'll find that p is the same thing as theta over 1 plus exponential theta. And we'll need this when we're coding in R. So you need to know how to go back and forth. And then we also have the function g. We also have the canonical link. Now, this is when we started talking about the Step 2 video, we decided to use the canonical link, which is theta equals y. And then we found what mu is, right? And then you could solve for y, and you would find that these two equations are the same. I just solved for y, and we'll need this, how to go from mu to y and y to mu in our R code. So that's why it's important understand these are the same equations. And then we also solve for d mu dy, okay? And then using these guys, you can find the weights. We found that the weight function, it simplifies. Instead of this being squared divided by v, since v equals this, basically it simplifies a little bit. So this is the weight function. Again, we discussed this in the Step 2 video in more detail. Lastly, you need to know the solution to a weighted least squares. You can find this, anywhere if you want to look up weighted least squares. This is the known solution. Okay, so where W is your diagonal matrix of weights. Also, you could set up this problem yourself and solve it, and verify that this is indeed the solution for this weighted least squares problem. Okay, so you'll need this. All right, so let's go ahead and pull up, let me see. I'm going to go ahead and pull up the paper, and I want to go to the right section. So this is the section we want to be reading through when we're coming up with our algorithm. Okay, so first we need to do is take your first approximation for mu equals z and calculate y from it. So that's why it's important that we know. Let me move this up. So we'll take mu equal to z, and then we'll calculate y. So that's why we need to know this relationship here. Okay. Then, once you've done that, then calculate w and set y equal to capital Y. So that's what we'll do. Okay, so we'll calculate W, and then we'll be able to solve for this, and then we'll be able to get our first estimate for the weighted least squares. And then once we have that first estimate, we can update what capital Y is, because we can go up here, and now that we have our first estimate, we can figure out capital Y based off of this equation here. And then once we have a new capital Y, we can find mu, and we can find d mu dy, we can find updated weights, we can find an updated solution. Once you have an updated solution, you can go back up here, find y, and you can see how this is an iterative process until you converge. Okay, so that's the idea. Now, there is a mention of the method might need slight modification to extreme values of z. And this will be our case because, so they mentioned the binomial distribution. Bernoulli is technically an example of the binomial distribution when n equals 1. So the number of trials equals 1. And so in this case, all of our data are going to be 0 and 1s. So they recommend that you go ahead and replace z with 1/2. And that's what we're going to do in our code. Okay? So yeah, I think with that, we are ready to go ahead and pull up R and start talking about the R code. Let me pull it up right here. Okay. Let me clean up my... Alright, so clean up my environment first. Okay, so now we need to, if we want to do this, let's go ahead and simulate some data. Now you could simulate data however you want. I decided that I'm going to simulate n equals 50, so 50 data points, and I set my betas to -1 and 1. So I have an intercept and then a slope, basically. And then I use just a random sampling of the numbers 1 through 5 for x1. You can do whatever you want. You could have used a normal distribution for x1. You could have, anything you want for x1, right? Or this is just an example. And then for x is basically, this is the data matrix. So I have that vector of 1s for the intercept, and then I have x1 for my slope. Okay, and then I'm calculating y from it. So let's go ahead and run this code. Okay. Now, since I'm using the canonical link, I can go ahead and set theta equal to y. So I'll run that. And then my probability of success, I can calculate that based off of theta. So this is, remember, we had this equation up here, right here. Okay. So this is all just in my simulating data. So making up data, basically. All right. Now I have my probability of success. I can simulate z. And this is the random binomial function in R. Okay. But the number of trials is 1. So that basically makes it a Bernoulli, random Bernoulli. All right. So you can, if I run this, you can see it's just a bunch of 0 and 1s. All right. Now I'm going to go ahead and use that GLM function that R has, okay, and show what R will give us the answer, right? Because R will do this automatically for me, and R found this to be my estimate of the intercept and then my estimate of the slope. Okay, and of course every time you run this code you're going to get different because this is based off of your random simulated data. Okay, so when you run this you'll get slightly different numbers there. Alright, so now what I want to do is I want to use the Nelder and Wedderburn's approach and see if I get the same thing that R calculated. That's what I'm interested in, right? I want to basically reproduce R's GLM result, okay? So the first thing I'm going to do is take my first approximation to mu equals z. Again, I can't do that because I have extreme values, so I'm just going to do 0.5s. Alright, so I'm going to get mu equals 0.5. Then I'm going to calculate y from it. Alright, so just a reminder, okay, this is the function for y once I have mu. So there it is right there. I'll calculate that. I'll run that piece of code. and then calculate W. So to calculate W, I'm going to calculate du dy first. Okay, and this code could definitely have been written more efficiently, but you know, I'm repeating pieces of information just because, you know, just to make sure it's really clear what's happening here. Okay, so now once I have d mu dy, that basically is what W is. But in my solution, I want a diagonal matrix, right? So what I'll do is I put all these K on the diagonal and then zeros everywhere else. And so you can see that's what I'm doing here when I set a diagonal matrix. You can print this, or see, I can double click on it, and you can see that's what it has. It's a diagonal matrix. Okay. 50 by 50 diagonal matrix. Okay, then I set little y equal to big Y. Let me run that. Okay, and then I can find my first approximation of my betas. So in R, when you find the inverse, you have to use the function solve. Okay, and then T means transpose. And so let's go ahead and run that. All right, and then I'm going to set my previous beta just to a bunch of ones. Okay, and then what I want to do is I want to run this until beta converges to something. So basically until the difference between the betas, the absolute difference is 0.001, less than 0.001. Okay, so let's see. So it will continue to run it. Sorry, yeah. So it'll continue to run this code while it's more than 0.01, and then 0.001, and then once it's less than that, it'll stop running the while loop. Okay. So first thing I want to do is go ahead and save my previous beta to whatever my current estimate is, and then I'll update my y based off of that, and then I'm going to update my mu based off that y, update d mu dy, and then update my weights, update what little y is, and then solve that weighted least squares estimate again. I'm going to print beta for the latest least squares every time I run it, just so you can see it changing and updating. And then so let's go ahead and do this while loop. Okay. Let's see. Should have printed every time. Let's go ahead and let me print it right. Oh, I think I ran something. So let me run this one more time. Okay. Yeah, I accidentally ran a piece of my while loop before running the whole loop. So there we go. Okay. So you can see it printed out each time. So let's see how close is this to what R came up with. So -2, 1, 3, 2, 7, and then positive 1, 2, 7, 7, 3. Yeah, you can see they're identical. So we basically have come up with a code that can recreate, you know, what R does in this GLM, you know, on this code that R already has. We basically have come up with what's behind, you know, what's behind it.